Generic reduction from external to swap regret. In this section, we give a black box reduction showing how any procedure A achieving good external regret can be used as a subroutine to achieve good swap regret as well. The high-level idea is as follows. See also figure 4.1. We will instantiate n copies A1, A2, A3 until AN of the external regret procedure. At each time step, these procedures will each give us a probability vector which we will combine in a particular way to produce our own probability vector P. When we receive a loss vector L, we will partition it among the n procedures, giving procedure AI a fraction Pi. Pi is our probability mass on action I. So that AI's belief about the loss of action J is the summations of Pi to the t times Lj to the t summing for all those t, and matches the cost that we would incur putting I's probability mass on J. In the proof, procedure AI will, in some sense, be responsible for ensuring low regret of the I to the J variety. The key to making this work is that we will be able to define the P's so that the sum of the losses of the procedures AI on their own loss vectors matches our overall true loss. Recall the definition of an R external regret procedure. Definition 4.14. An R external regret procedure A guarantees that for any sequence of T losses L to the T and for any action J which is chosen in 1, 2, 3 until N, we have L A to the T equals to the summations of L A to the T. A is the regret procedure, and we're summing for all those t starting from 1 to capital T, which is less than equals to the summations of Lj to the T plus R, if we're summing for all those t starting from 1 to capital T, which is equals to Lj to the T plus R. We assume that we have n copies 1, 2, 3, A1, A2, A3 until AN of an R external regret procedure. We combined the n procedures to one master procedure H as follows. At each time step T, each procedure AI outputs a distribution Qi to the T, where Qi j to the T is the fraction it assigns action J. We compute a single distribution P to the T such that Pj to the T equals to the summations of Pi to the T times Qij to the T, summing for all those I. That is, P to the T equals to P to the T times Q to the T, where P to the T is our distribution and Q to the T is the matrix of Qij to the T. We can view P to the T as a stationary distribution of the Markov process defined by Q to the T, and it is well known that such a P to the T exists and is efficiently computable. For intuition into this choice of P to the T, notice that it implies we can consider action selection in two equivalent ways. The first is simply using the distribution P to the T to select action J with probability Pj to the T. The second is to select the procedure AI with the probability Pi to the T and then to use AI to select the action, which produces distribution P to the T times Q to the T. When the adversary returns the loss vector L to the T, we return to each AI the loss vector Pi times L to the T. So, procedure AI experiences loss of Pi to the T times L to the T times Qi to the T, which is Pi to the T times Qi to the T times L to the T. Since AI is an R external regret procedure for any action J, we have the summations of Pi to the T of times Qi to the T times L to the T, summing for all those T starting from 1 to capital T, which is less than equals to the summations if we take out the Qi to the T term. The summations of Pi to the T times Lj to the T summing for all those T starting from 1 to capital T plus R. If we sum the losses of the n procedures at a given time T, we get that the summations of Pi to the T times Qi to the T times L to the T is equals to P to the T times capital T Q to the T times L to the T, where P to the T is the row vector of our distribution. Capital to the T is the matrix of a Qij to the T, and L to the T is viewed as a column vector. By designing of P to the T, we have P to the T times capital Q to the T equals to P to the T. So the sum of the perceived losses of the n procedures is equal to our actual loss P to the T times L to the T. Therefore, summing equation 4.1 over all n procedures, the left-hand side sums to L h to the T, where h is our master online procedure. Since the right-hand side of equation 4.1 holds for any j, we have that for any function f which maps from 1 to 3 until n to 1 to 3 until n, LH to the T is less than or equal to the doubling summations, with the outer summation summing with the I starting from 1 to capital N, and the inner summation summing with the T starting from 1 to capital T of the term Pi to the T times L f of I to the T plus N times R, which is equals to LH f to the T plus N times R. Therefore, we have proven the following theorem. Theorem 4.15. Given an R external regret procedure, the master online procedure H has the following guarantee. For every function f which maps from 1 to 3 until n to 1 to 3 until n, LH is less than or equals to LHF plus NR, i.e. the swap regret of H is at most NR. Using theorem 4.6, we can immediately derive the following corollary. Corollary 4.16. There exists an online algorithm H such that for every function f which maps from 1 to 3 until n to 1 to 3 until n, we have that LH is less than or equals to LHF plus big O of n times square root of t times log n, i.e. the swap regret of H is at most big O of n times the square root of t times log n. Remark, see exercise 4.6 for an improvement to big O of a square root of n times t log n.